Okay, so we've reached a point where we now have a relationship between the activity of component 1 of our solvent and the molality of the solution. And this would hold if everything behaved ideally, right? So we said if the solution is sufficiently dilute. Now, in this case, usually this will not hold. And so we introduce a new variable that we call the osmotic coefficient, phi. That's the Greek letter phi, divided, let's try this again, divided by 55.506 moles per kilogram. And what phi tells us, this takes into account, this is the non-ideal behavior. And this is what's the discrepancy between our measured activity that we measure from the vapor pressure versus what the actual molality of the solution is. And so this is, again, the name of this is the osmotic coefficient. And my hand just keeps messing up here. All right. There we go. Okay, so the osmotic coefficient. And so what we can do is we can actually measure this osmotic coefficient, because we can measure, once my board moves here, we can measure the activity of our solvent, and we can measure the molality of our solute, or prepared known molality solutions. And that will let us calculate the osmotic coefficient. Now, I'm going to skip a few steps in terms of the derivation here. You can go into section 25-2 in your textbook to get more of the details here. And my screen has frozen, so that's not great. But we can relate this osmotic coefficient to the activity coefficient. And it uses the Gibbs-Duhem equation, this relationship between our chemical potentials of component 1 and component 2. So I'll just write down the final equation that we get is that d log of the activity coefficient in terms of molality is equal to d phi. Phi here is the osmotic coefficient, plus phi minus 1 over the molality, d molality. Okay, and so then we have to integrate this. So we integrate from m equals 0 up to some arbitrary value of the molality on both sides. So we need to integrate here. And my screen still won't move around, so I'm not running out of space here. But we'll get that log of gamma to m is equal to phi minus 1, because when m is equal to 0, phi is equal to 1, plus this integral on the right here. So 0 to m, phi minus 1 over m dm. And this may look familiar. This is similar to the equation that we got for fugacity coefficients. That we have, if we measure some property that measures the non-ideality. In the case of fugacity coefficients, it was the compressibility factor. Here it's the osmotic coefficient. And we measure that difference, phi minus 1. We had z minus 1 for the gases for fugacity, divided by the concentration. There it was the pressure. But this allows us to find the activity coefficient. And then we can use that activity coefficient to find activities and use that in place of concentrations everywhere we're looking at equilibria. In the next video, we'll look at some plots to sort of hopefully make a little bit more sense out of this, and what this might look like in practice for a particular solution.